Hello friends, in the last few videos we have discussed about sequences. Now we discuss about series. Friends, in series sequences are used. Therefore, for series we have to study about sequences. So I request you, before watching this video, you should watch about sequences. Here we introduce series, we define series, and uh, we prove one theorem and examples of series. We have discussed about a sequences. Sequence is a function from set of natural number to a set of real number. If we consider a sequence Sn equal to minus 1 raised to n, in this sequence, if we add the terms of the sequences minus 1 plus 1, minus 1 plus 1, minus 1 plus 1 equal to like this, minus 1 plus 1 plus minus 1 plus 1 plus, we get 0 plus 0 plus 0, and hence we get a 0. Or if we add like this, minus 1 plus minus 1 plus 1 minus 1 plus 1 minus 1 plus, then we get minus 1. If we add the sequence like this, first if we write this as a plus 1 plus minus 1 plus 1 plus minus 1 plus 1 plus, we get minus 1. In this sequence, the addition of infinite terms, or if we write all the terms of the sequences here, summation, if we take the summation of all the terms of the sequences, then we get three different answers. One is a 0, one is a minus 1, and plus 1. These are the three different answers of summations of minus 1 raised to n, and this is absurd thing. Therefore we need a knowledge of this summation of this term, summation of minus 1 raised to n, or more precisely, if we write it as my summation of uh, the terms u n, then this is called as a infinite series. This is called as a infinite series. Now in this chapter we will see how to add the infinite terms of the series, and uh, there are various tests of convergence of a series. So friends, series are useful to get the answer of this question, how to add the terms of the sequences, and it gives us a definite answer. As a mathematicians, we should know how to add these things and how we get a concrete answer to this type of questions. So in this chapter of infinite series we will learn about how to add this series. So if this summation un is an infinite series, then these are the uh, terms of the sequences. If u1, u2, u3, dash dash dash, these are the terms of the sequences, then summation of this term is called as a series. Sometimes we denote this series by this simple notation, summation un or sometimes we write it as summation of n is equal to 1 to infinity. Here if we omit this n equal to 1 to infinity and if we write summation of un, it is the same meaning as this term summation of n is equal to 1 to infinity. And hence if we take this series summation of un, suppose my series is summation of un, this is my series, suppose summation of un, then the sequence is u1, u2, u3 dash dash dash. These are the terms of the sequences. So depending on these terms we form another sequence. Suppose s1 equal to u1, s2 equal to u1 plus u2, s3 equal to u1 plus u2 plus u3, or more generally Sn equal to u1 plus u2 plus u3 plus un. Then we get a sequence Sn, and this sequence is called as a sequence of partial sum. It is called as a sequence of partial sum of series, sequence of partial sum of series. So using this sequence of partial sums we convert whole series into a sequence, and uh, our knowledge of sequence will be helpful to get the knowledge about series. When the sequence of partial sum Sn converges, the series is convergent. When this sequence is divergent, then the series is also divergent. And therefore in this regard the sequence of partial sum of the series play an important role in the infinite series. When the sequence convergent, the series is convergent. When the sequence of partial sum is divergent, then the series is a divergent. When the sequence of partial sum is isolate, then the series is also isolate. According to this nature of the sequence of partial sum of a series, of a sequence, the series is a convergent, divergent, or oscillating series. And hence friend, this nature of sequence of partial sum will play a central role in the infinite series. Now we see that the terms of the series also helpful to recognize whether the series is a convergent or divergent. As I have said, if the sequence of partial sum is convergent, suppose this sequence is convergent, then the sum of the series is equal to L. In that case, we can write this whole summation of the series is equal to L. Now, let us see one theorem. The necessary condition, the statement of the theorem is necessary condition. Necessary. I am writing this statement on necessary condition for convergence for conver convergence of an infinite series of an infinite series summation un is that limit of un n tends to infinity equal to 0. So here if the nth term of the series is tends to 0, then the infinite series converges. Let us see the proof of this series. I have told that the sequence of partial sum play a central role in defining a convergence of a series. Therefore, here we take Sn equal to, suppose, u1 plus u2 plus un. Then we can easily calculate Sn minus 1, which contain n minus 1 term u1 plus u2 plus un minus 1. Then we see that Sn minus 1, this will be u1 plus u2 plus un, and minus these terms, so minus u1 minus u2 and up to minus un minus 1. u1 u1 u2 u2 get cancelled and we remain only the terms un. Now if we take the limit of this, limit of here un tends to infinity, so this will be the limit of Sn minus limit of Sn minus 1. Now you can see that here the we have taken the series is a convergent series, and therefore here the sequence is a convergent sequence. Since the series is a convergent, summation un is convergent, therefore the sequence Sn is also convergent, and it converges to, suppose, that means limit of Sn equal to S, say, as limit of Sn equal to S, limit of Sn minus 1 is also equal to S. So here you can see that what we get, S minus S equal to 0, and hence whenever the series converges, the limit of a un term, nth term, is equal to 0. Friends, the converse of this series theorem is always not true. Whenever, if the limit of un equal to 0, then the series un may converge, may diverge. But whenever the series is converges, this theorem tells that whenever series is a convergent, limit of un is definitely 0. But the converse of this part, that is, if the limit of un equal to 0, then we do not have idea about summation of un. It may converge, it may diverge. Okay, but using this theorem, we say that if limit of un not equal to 0, then definitely summation of series is a not convergent, it is a divergent, is not convergent. Whenever limit of un not equal to 0, we get that summation of un is not convergent series. So let us see how these theorems work using few examples. Suppose, so in let us take an example, show that the the series 1 by 2 plus 2 by 3 plus 3 by 4 plus is not convergent, is not convergent. As we have seen that if limit is not equal to 0, limit of un not equal to 0, then the series is divergent. Now we use that theorem to prove this. You can easily see that here the term un equal to n divided by n plus 1. This is my un in this case here. So we take the limit of this term, limit of un, as n tends to infinity. This is equal to limit of n divided by n plus 1, n tends to infinity. This is equal to limit of, we write this term as taking this n in the denominator, we write this as 1 divided by 1 plus 1 by n, and we know that limit of 1 by n is 0. So here we get 1 in the limit, which is not equal to 0, and therefore the series is a divergent series. Now friends, we are familiar with the Cauchy's criteria of sequences. What is that? Necessary and sufficient condition for the convergence of a series is summation Sn minus Sm is less than epsilon for all n comma m greater than equal to some fixed number for capital N, and for epsilon greater than 0. This is the Cauchy's criteria. So here the Cauchy's general principle of convergence of a series is also depend on these terms, that is a necessary and sufficient condition, a necessary and sufficient condition, necessary and sufficient condition, necessary and sufficient condition. I am writing this to get the statement of Cauchy's criteria, general principle for convergence of a series. For convergence, for convergence of an infinite series, of an infinite series, infinite series, of an infinite series, summation un is that, is that the sequence, the sequence, sequence of its partial sum, sequence of its partial sum. uh, what is the, this is the sequence of partial sum is convergent. This is the Cauchy's criteria. Necessary and sufficient condition for convergence of an infinite series summation un is that the sequence of its partial sum convergence. So we convert this criteria into a theorem, and we prove that theorem, which has a very easy steps, and depending on the sequence here, the statement of the theorem is that a series, a series summation un converges, summation un converges if and only if to each, to each epsilon greater than 0 there exists, there exists a positive integer, there exists a positive integer m such that, there exists a positive integer m such that mod of un plus 1 plus un plus 2 plus un plus p is less than epsilon for all n greater than equal to m and p greater than equal to 1. Okay, so friend, remember the Cauchy's criteria of convergence. Cauchy, This is the Cauchy's general principle. General principle. General principle of convergence of convergence for a sequence. What is that? Uh, that is the sequence SN of partial sum. We are taking the sequence of partial sums of the series summation un if and only if to each epsilon there exists a positive integer. There exists a positive integer positive integer m such that mod of Sn plus p minus Sn less than epsilon for all n greater than equal to m and p greater than equal to 1. So this is an logical AND. We are using the logical AND term here. So this is about Cauchy's criteria for convergence of a sequence. Now we know that what is a SN equal to u1 plus u2 plus un, and from this Sn plus p equal to u1 plus un plus 1 plus un plus 2 plus un plus p. This is the Sn plus p terms. Now Sn plus p minus Sn equal to, we get un plus 1 plus un plus 2 plus un plus p. Now substituting here mod of Sn plus p minus Sn equal to here mod of un plus 1 plus un plus 2 plus un plus p, and this is less than epsilon for all n greater than equal to m and p greater than equal to 1. Okay, so here we have proved that the series is convergent if and only if un plus 1 plus un plus 2 plus un plus p is less than epsilon. Now see examples on Cauchy's criteria. We show that the series show that show that the series summation 1 by n does not does not converges does not converges. We prove this by contradiction. So let us prove this by contradiction. If possible, it is a convergent. If possible, summation 1 by n is convergent. If it is convergent, then we can apply Cauchy's criteria, and we see that it is true for every epsilon. So let us take here epsilon equal to 1 by 2. 1 by 2. So let us choose this value epsilon equal to 1 by 2, and for this particular value there exists a positive integer. There exists a positive integer m such that according to that general principle we have mod of un plus 1, that will be 1 plus n plus 1 plus n plus 2 plus 1 divided by n plus p is less than epsilon. Epsilon Here we will write at the end the epsilon value. So let me write first general terms. So this is the Cauchy's criteria. Okay. Now let us put particular value of n and m. If we take particular value of n is equal to m and also p is equal to m, then you can see that here 1 divided by n plus 1 plus 1 divided by n plus 2 plus 1 divided by n plus p, this will be 1 divided by m plus 1 plus 1 divided by m plus 2 plus 1 divided by m plus m. Now friends, you can see that m is less than 2m, or m plus 1 is less than 2m. So 1 divided by m plus 1 is greater than 1 divided by 2m. Similarly, m plus 2 is less than 1 divided by 2m, and hence 1 divided by m plus 2 is greater than 1 divided by 2m. For this, using this, we replace this term by 1 divided by 2m, plus this will be replaced by 1 divided by 2m plus 1 divided by 2m. How many times? M times. And everywhere we have replaced the smaller terms, and hence this sum will be less than this second sum. Now you can see that this is equal to m times 1 divided by 2m, and m get cancel. So here we get that 1 divided by n plus 1 plus 1 divided by n plus 2 plus 1 divided by n plus p is greater than 1 by 2, but it is less than 1 by 2 for every epsilon, and hence this is a contradiction, and this shows that this series 1 divided by 1 divided by n is not a convergent series. And you can check that what is the un equal to 1 by n. If we take the limit of un equal to limit of 1 by n, and this is equal to 0. So this is a example here which gives that here the limit of un is not give a definite answer about the convergence of a series. So we cannot take the converse of that theorem, where the series is convergent when the limit of un equal to 0 is not always proved. But whenever the series is convergent, the limit of un is equal to 0.